Okay. Hi, everyone.
Should I look into the camera or just look at you?
As you wish.
Okay.
You can switch
All
between both
right.
things.
Good.
So this will be, as I commented before, an interview for, especially for my students there in Chile. It will be undergraduate students, but also graduate students. So in this interview, I would like to ask you some of the things that you have been developing during all these years.
Good.
Well, students, as you know, I'm here with Rudy Marcus, my postdoctoral mentor at Caltech. And first of well, Rudy was awarded the Nobel Prize in Chemistry in 1992 because of his contribution to the theory of the electron transfer reactions.
Right.
So the first question is about that.
Okay.
How would you explain Marcos theory in your own words, in Rudy Marcos words?
Right.
Uh-huh.
Well, there's a standard theory for chemical reactions in general called transition state theory, which relates the barrier to reaction, the energy barrier, the free energy barrier, to various thermodynamic and other properties, including the properties of the transition state. But that's a kind of a general kind of theory. But there are these electron transfer reactions which have some very specific properties that one needs a more specialized theory to put in those specific properties. Mm-hmm. And the specific property that's involved is this. If an electron jumps from one molecule to the other, then that jump normally, when it happens, takes such a short time that the various vibrations don't have time to respond to the change. Mm-hmm. Yeah. Now, when you jump from one reactant to the other, you now have a force field around each of the reactants, which is very different from just before, and that means the energies are very different. So somehow you have to, in the transfer, the energy should be the same before and after. You have to conserve energy during the actual transfer. And what I showed that in order to do so, you had to have fluctuations of the environment, including the vibrations, fluctuations in that precede the electron transfer, so that when the jump occurs, actually you've conserved energy.
That's right. Yeah.
So, and the key thing about the theory is how do you study those fluctuations? Mm-hmm. What kind of a formalism do you develop with the interaction of the charges of the ions with the solvent? And remember, it's it's a fluctuation thing. How do you put all of that in there? So that's what the theory involved, and the idea, the whole idea, was stimulated by my reading a paper around 55 or so of a symposium that had taken place in 1952. And in that symposium, it was on electron transfer reactions, and Bill Libby, who later won the Nobel Prize for radiocarbon dating, mentioned, this when the electron jumps, there's no time for anything else to happen. So, and he formulated a theory, which he applied what's called the Frank-Condon principle to that. But he didn't realize there had to be changes going on before or after, before the electron could jump. So he had a theory. He brought out the important idea of applying the Frank-Condon principle of when an electron jumps. Nuclei don't have time to do anything. Mm-hmm. But when I looked at, so I was very excited when I saw his paper, which I saw just by going to the library. I used to go to the library very often and look through journals, even older journals. And I was very excited when I saw application of the Frank-Condon principle. And then I realized that what he didn't take into account is that there had to be changes before the electron could jump, otherwise you would violate the law of conservation of energy. Mm-hmm. So then I figured out a way of how to treat those fluctuations based upon using some information that I had from previous work that I'd done that had nothing to do with electron transfers.
With electrolytes, right?
That's right. It was related to the free energy, the polyelectrolytes, and I became very familiar with the various electrostatic contributions. So I built on that knowledge, and without that knowledge, I probably wouldn't have been able to have done this. And I acquired that knowledge actually in response to a graduate student's question. This is a course that I was that I was teaching, and this chap was working for somebody else, doing experiments on what's called polyelectrolytes, and he asked me whether a particular theory that we were teaching in statistical mechanics would be applicable to his polyelectrolytes. And I thought about, yes, it would be. That had nothing to do with electron transfer. That had everything to do, though, with free energy of ions interacting with each other and with the solvent and so on. So I learned a lot of that in a fundamental way, so that when this problem came up, I had the necessary background to treat it. And also, I had read quite a bit about related problems in physics. The related problem in physics at the time was a charged particle going through a crystal and polarizing the crystal. So the stage of polarization is not equilibrium. It's sort of a it's adjusting to the transient motion. So I had read that literature, so that helped formulate my ideas on electron transfer.
And
but it was bringing together a combination of different things. I've often thought, is there some underlying feature to research that I've done? And I think quite often it's a matter of connecting the dots.
That's right.
First of all, identifying the dots, then finding a way of connecting it.
And what is the role of the solvent in your formalin in the equation?
The role of the solvent is that if it's a polar solvent, then it interacts strongly with the ions, and that means if you have a certain ionic charge as the beginning, then you have typical orientation of the polar molecules towards the ion. But if you transfer the charge, that orientation or typical orientations is not appropriate to the new charges. So that means you had to have fluctuations in those orientations, and you had to have a way of describing the free energy associated with those fluctuations, and you had to have a way of describing what the fluctuations are, and all of that I did in the electron transfer.
But in the way you representation of the formalins, you have these two parabolas.
Oh, right? Yeah, those are free energy parabolas.
Yeah.
Now, you can, if you want, you can regard them in an overly simplified model as just simple vibrations.
Simple vibration.
But basically, where they came from was that is the free energy of the system as a function of some fluctuation coordinate, and the fact that the free energy is a quadratic function of some coordinate, I didn't realize at the time, but I was making use of what in statistical mechanics is called a cumulative expansion and stopping at the second order cumulative. I never realized that at the time, but I forget who pointed out to me that that's what I was doing without knowing.
I see.
I didn't know why it worked. I was doing something that is equivalent to what's called a cumulative expansion in statistical mechanics. So sometimes, one proceeds with a certain degree of ignorance, but that's okay.
Okay, that's good. To know that. So, but then the reaction coordinate in that representation is vibrational.
Well, it depends. It's a combination of things. Because there's certainly a vibrational component.
Yeah.
Typically, for example, if you have an ion with, say, 6 water molecules or 6 of anything around it, is one example, and similarly over here, then you have these breathing vibrations. And typically, one of the things that's different of the ion, how it depends on its charge, the charge of the ion, is the equilibrium bond length. So, for example, if you have a self-exchange reaction, cobalt hexamine plus 2, cobalt hexamine plus 3, then you have a symmetric vibration that can change to the appropriate equilibrium distance there.
Oh,
So
okay.
often it's just certain selective vibrations,
I see.
collective vibrations that are involved. That's the vibrational part. But then there's also the solvational part outside of the first coordinate.
That is also included in the reaction coordinate.
Right.
I see.
So there are two parts.
Two
That's
parts.
right.
I see.
And in the first part, in the first paper I wrote on it, I focused mainly on the solvation part, not counting the coordination shell. And then a couple of years later, I think it was 1959, 3 years later, I wrote something, or maybe it's a little bit earlier than that, wrote something which had in the other part.
I see.
Yeah.
I see.
But I started off first with the behavior outside the first coordination shell.
I see. So this is referred to the outer sphere.
Yes, that's right. Yeah. Well, the outer sphere refers to the fact that you've got no chemical bond between the two reactants. That's right.
So it's non-adiabatic, basically, electron transfer
It's
reaction.
often non-adiabatic. Perhaps most of them are non-adiabatic, maybe just weakly so, but and of course the question is now, when you get very, very fast electron transfers, might some of them be adiabatic? There's so much coupling between them.
So how should develop the part of the inner sphere electron transfer reaction?
The non-adiabatic?
Yeah, no, not adiabatic.
No, that's connected with the extent of electron coupling. It's purely an electron coupling question. The extent of electron coupling between the orbital involved here and the orbital involved there, independently of everything else.
Right. Okay.
Yeah. And probably most of the reactions tend to be non-adiabatic or near there, but there's some which are ultra fast, and it may be there the interaction is so strong that you might have to use a somewhat different formalism.
Yeah. But then the format of your theory was also applied to group transfers, like proton transfer, metacation transfer.
That in science, there's an advantage of being venturesome. And the equations I derived relating free energy to standard free energy reaction were derived for electron transfers. Now, Norman Sutton, a wonderful experimentalist, said that he's going to apply it instead to an atom transfer, electron transfer reaction. It really involved transfer of an atom rather than an ion. And the equations seemed to work. And so then in 1968, I wrote a paper showing how some aspects of the theory, that quadratic expression, could be used to treat not only electron transfers, but to treat atom transfers and group transfers and so on. And one can make certain predictions on relating what's called cross reactions to relating experiments on those to to the self-exchange reaction, things like that. And we did, and actually the best tests, the most successful tests of something that we derived called cross relation was for something that had nothing to do with electron transfers. But I used a different model then in 1968 to show how you could get an expression that in certain respects looked like this. Not quite, a little bit different, especially at very large delta G zeros, but it looked very similar, and so various people tested that expression.
That's right.
The cross relation is called.
And what happens, for instance, because Marcus' equation is a free energy relationship relating thermodynamics with kinetics.
That's the whole thing. Yes.
Yeah, but in reaction, when you have the formation and cleavage of bonds, you use usually the Eyring-Polanyi equation from transition state theory. But and you have other real energy relationships like Hammett equation, stuff like that. But sometimes it's very helpful to use also your formula.
And one of the things I wanted to do was, and I started on it, but I never finished it, and I don't know if I could have gotten, was to ask, if you take the Hammett
Yeah.
equation, the rho sigma formalism.
Yeah. That's right.
Is there some way one could translate that as a kind of special case of this other thing?
Yeah.
And so I started work on that and somehow got involved with other problems.
Okay.
I'd like to return to it sometime.
Yeah.
But it's possible that one might be able to relate. Remember, the Hammett equation involves not only rho sigma, but I think sigma plus, sigma minus.
Yeah, that's right.
And so I was wondering whether maybe I might be able to do something, relate the two types of theory. And actually, I would have loved to have done that because it turned out that the external examiner for my thesis was Lewis Hammett.
Oh, I see. Okay.
At those, I don't know what it is now, but it was certainly in Canada, the research advisor had to ask somebody to be an external examiner. And in fact, in England, they still have that. At least I know Alan, who's in the film field and not chemistry, but I mean, he's involved in either being an external examiner or some of his students are examined by a thesis external examiner. So they still have that. I mean, we don't have that here, but maybe they still have it in Canada. I don't know.
I see. Well, that's great. That's very interesting. Yeah.
I never knew what Hammett thought about the things. So.
Yeah. And also, another very, very important aspect in your theory is about this inverted region.
Oh, yeah,
So
that's right. That's right. And when you use the parabolas to describe things, then it's very clear how the inverted region comes about. That if you have two parabolas and you make the products increasingly stable, and eventually you get the zero barrier, and then it starts climbing up the other side. And so that was a prediction that we made. And for 25 years, nobody had verified it. Now, a consequence of it is that some reactions, to avoid that, might form products in an electronically excited state to get rid of all that excess energy. So we showed in the 1960s how you could get chemiluminescent electron transfer reactions. And Al Bard, who studied those, is often fond of saying, and it's true, that was the first indirect verification of this inverted region prediction. Because there are some reactions, chemiluminescent, where he got 100% formation in excited states because the inverted effect, they couldn't form the ground state, so they formed the excited state. But it wasn't until 1985 until several people, Calcutta, John Miller, Gerhard Kloss, showed by an actual example that you get the inverted region. And now many people have showed the inverted region.
Yeah, but that is a
very often.
Breakthrough
The one theoretician even wrote a paper saying that you can't have the inverted region during this period. But I never felt. I mean, even though the prediction was there and there really wasn't verification, I never felt any doubt. I mean, there are a lot of things certainly that I've been involved in that I wouldn't stake my life on, but that's one of them I would.
I see. Okay.
So it didn't really bother me, even though it should have maybe, but it didn't.
Yeah.
You know.
Oh, but it's great.
Because I felt it was right.
Yeah. The other theory that you are also have been developing is the RQM, right? The Rice-Ransperger-Kastelmarkus theory. Can you explain a little?
Sure. That's, as you know, a theory where you have a molecule with a lot of energy. Maybe the energy's been put there thermally, or maybe by a photoexcitation. Anyways, you got a lot of vibrational energy in the molecule, and then the molecule maybe breaks up or isomerizes, rearranges, and the rate of that happening depends upon how much excess energy it has. And so this was a theory that was my first theoretical work. I went to work on a postdoc with Oscar Rice, and he suggested that I work on unimolecular reaction rate theory without, specifying much in detail. And so, having gone into theoretical work with practically no background in theory, I was excited. I really was excited. So I read about everything that you can imagine on reaction rates. Well, after all, the details only started around 1920, and this was 1949. So so I really read a lot of that, and then I read a lot about what had been done on unimolecular reactions, these reactions, and a lot had been done during the 1920s, and there was a famous theory, RRK theory, to treat that. But that was a theory that was developed just before quantum mechanics, and certainly before transition state theory, because that was developed by Eyring and some others in 1935. So the question was, could I take the RRK theory and bring it up to date? Somehow put in the extra knowledge of quantum mechanics, put in the extra knowledge of potential energy services, somehow blend it to the original statistical ideas. And so I read practically everything been written related to that. Okay. So when I saw something I liked, I took it. If I didn't like something, I threw it out, and so on. And without realizing it, I built up RKM theory. I didn't call it RKM theory. Seymour Rabinovich, who did a lot of experiments related to it, testing it, called it that. And so the name stuck. But it was really a matter of putting together the old theory, the RRK theory, and the various quantum mechanics, the potential energy services that have been done since, and the transition. Sort of matter of just taking little bits here and there, stirring them up, and the theory came out. And one interesting thing is the first paper that I wrote on it appeared in 1951. And in it, for the expression for the rate as a function of energy, I had an infinite series. And then I went up to Brooklyn Poly. I had got a position there. Went up to Brooklyn Poly and wrote 4 papers related to RKM. And I sent them to Rice, and I put his name on, and each of them. And he took his name off, and said he hadn't done anything. And it's true, this is stuff I'd really done on my own. The first paper I published with him, but there were these 4 papers. And I thought at the time, well, he doesn't think they're good enough. Anyways, it's just that was his way, if he didn't think he'd put anything in. And this was largely work I'd done up at Brooklyn Poly. So I wrote those 4 papers, and that's how it came about. It was just a matter of taking RK theory and adding to it the knowledge of potential energy service, the knowledge of transition state theory, and certain properties associated with crossing the transition state theory, and putting it together with some of the rudiments of the old RRK theory. So it's just a matter of putting bits and pieces together, and
that's great work. And do you think there is still room to do additional things in that specific field?
Well, yes would be, it makes a statistical assumption, statistical redistribution. And if you get to very short times, very high energies, then there may not be time for. And so certainly, when a point comes when the circulation of the energy is non-statistical, and that may be about 100 femtoseconds according to some estimates, then you would definitely need another theory there. And as far as the theory itself, people have combined it with detailed calculations of potential energy surfaces. Before we just guessed at things. What does a transition state look like? It has maybe some bending vibrations instead of rotations and things. It was very, very approximate. But they were able to just take the expressions, make the detailed surface potential energy calculations, make the detailed counting of states and things like that. And so they're able to put in modern computer results, just like people have done in electron transfer too. Like David Chandler, the work that he did in a fundamental way on molecular treatment and showing that yes, you get the problems actually. You get the problems.
Now I'm coming back to the theory of electron transfer reactions. What about the relationship that there is with these formalisms with the bond energy, bond order formalisms?
What they have in common, they have only one thing in common. There's a kind of give and take. You form a transition state, which is sort of a mixture of the old and the new. So configurations are in between. In the bond energy, bond order, you have one bond stretching, another bond getting smaller, and eventually you form the new bonds. So it's changes going on in both, and one thing is happening one simultaneously, something's happening the other. In the case of electron transfer, it's reorganization and vibrational changes. In the case of this Vibo thing, it's a matter of bond stretching and bond compressing, eventually breaking, etc. So it's kind of give and take. And so, for example, if you consider a reaction with delta G0 equals 0, just to put things there, then this give and take lowers the energy barrier for electron transfer by a factor of 4. In other words, if you have the parabolas, if you excite it up vertically, no reorganization, that'd be 4 times the barrier is at the intersection. In the case of the Vibo thing, the barrier is 10% of what it would be, roughly, 10, 12%. So 25%, 10, 12%. So the main thing is that when there's give and take, in either case, you can lower the barrier, you see, for an electron transfer.
The other question, well, related to the one that I asked before, but for example, many people develop this scheme of energy partitions to try to have this activation strength for the activation barrier. And on the other hand, you have the electronic effects, like the electronic coupling.
You have to take into account both,
but in some way, people try to visualize this with Markov theory in some way because it's very easy to visualize the reaction with your formula.
Right.
But it is possible to do it analytically, or there is a problem with the reaction coordinate?
Well, it depends what you want to do. You can always fit the equations in some way or another using some information. In some cases, when you want to really know what the reaction coordinate is, either you use intuition or you use results of calculation. For example, if you have a hexammonium complex here and a hexammonium complex there, then typically the symmetric stretching is the main thing that differs in the two cases, different equilibrium positions. So the reaction coordinate is a combination of this symmetric stretching and this symmetric stretching. That's an example of a specific thing. But in each case, by doing detailed enough computations, one could sort all that out.
Because the same thing when, for example, when I think in the conical intersection in this formula.
Now that introduces a new element.
But that can